Welcome students, here I come back again, but this time I have a plan to take up a module on survey sampling, techniques and inferential problems. We will make a quick review of what you already know from undergraduate studies, namely simple random sampling with and without replacement. Then we will go to topics in deep directions in other aspects, mainly talking about stratified sampling, etc. So, this time I have with me Mr. Samopriyo Basu. He is a Masters in Statistics degree holder from Calcutta University. He will be impersonating as the name suggested in the text, SSG Subhra Shankar Ghosh, and I am Professor Sinha. I will be impersonating as Bikram Sahai. So, here we start our discourse on survey sampling. There are 17 modules. In every module, as usual, we have some texts followed by some short answer questions and multiple choice questions. So, we will start our discussion on module number 1. So, let us get started with module 1, wherein we talk about simple random sampling with and without replacement. We plan to discuss this as one of the most commonly talked about sampling procedures, simple random sampling with or without replacement. I am sure all of you have a fairly good idea about it.
Under SRSWR sampling from a population of capital N units and involving a sample size of small n, altogether there are n to the power of small n possible samples, and we attribute equal chance to each sample. We may also note that under WR sampling, small n is not necessarily smaller than capital N, though in reality we work with small n much smaller than capital N. Sampling may be accomplished by using a table of random numbers. The samples may or may not involve all distinct units. There may be repeat units, and there we talk about the number of distinct units in the sample, denoted by nu. For estimation purposes, for estimation of the population mean, we may use the observations on the steady character, say y, including repeats or just the distinct units, each one used only once. Accordingly, we may use two different notations, small y bar for the mean based on all n observations, including repeats, and small y bar asterisk for the mean of new distinct units. We know, moreover, both y bar and y bar asterisk are unbiased for the population mean capital Y bar, and that variance of small y bar is more than the variance of small y bar asterisk. Hence, we should use the sample mean based on distinct units for estimation of the population mean capital Y bar. I'm not sure if I can write down the expression for variance of small y bar asterisk, and if I know a technical proof of 2 above.
Well, what you know is good enough to get a head start. In a way, I won't repeat what you have already said or stated. Still, for the sake of completeness, easy matters first. Under SRSWR capital N small n sampling, this is the usual notation, meaning thereby that capital N is the total number of units in the population, small n is the sample size, and SRSWR is the good old notation for simple random sampling without replacement. Over there, a sample is a random realization of 1 out of all capital N2's small n possible n pools of n distinct units out of capital N units in the population. We may note in passing that for without replacement sampling, small n is necessarily smaller than capital N. In fact, as you said, in all applications, small n is much less than capital N. The units, after selection through a randomization mechanism, applying sort of random number tables or even otherwise, the units are arranged in increasing order of their serial numbers, because every unit in the population is supposed to have a unique serial number attached to it, and the serial numbers are generally 1, 2, 3, etc. up to capital N. So, whenever we select a sample of small n units through appropriate randomization, the serial numbers are shown in increasing order. Further, the sample mean small y bar serves as an unbiased estimate of the population mean capital Y bar, as you said rightly, and moreover the sample variance small s square also serves as an unbiased estimate of the population variance capital S square. The point to note is, you may be knowing already, that both small s square and capital S square are defined with divisors one less than the number of observations involved in the computations. Therefore, for small s square, the divisor is small n minus 1, and for capital S square, the divisor is capital N minus 1. On the other hand, under with replacement sampling, SRS WR capital N small n, that means simple random sampling with replacement from a population of size capital N, the sample size being small n, a sample is a random realization of the sample frequency counts F1, F2, F capital N of the capital N population units marked as 1, 2, 3 up to capital N. So this is something that needs some kind of explanation. Whenever we are taking a random sample with replacement, small n times we are drawing samples from the population, there is a possibility of repeat. So repeat means there is a frequency count coming. So all the capital N units, in a way, they have associated frequency counts in my random realization of size small n. And these small fi's, these are non-negative integers, they add up to small n, the sample size. Therefore, you have a random realization of the sample frequency counts F1, F2, F capital N of the capital N units in the population. In a sense, therefore, the sample mean y bar based on all n observations, including the repeated units, can be expressed as y bar equal to summation fi yi over little n. So the fi is the frequency and yi is the corresponding value. Note that if fi is 0, that particular unit has not come up in the sample, therefore corresponding yi is not observable, and hence fi into yi, that contributes 0 to the computation of y bar. So this small y bar is computed based on every fi which is greater than or equal to 1. That means the units which have shown up actually in our random sample. And for those units, we get the corresponding observation y sub I. And because we are talking about the sample mean based on all small n observations including repeats, yi gets naturally a weight of fi. So this is my weighted mean summation fi yi over little n. So even though we are writing summation over I equal to 1 to capital N, it makes no difference writing I belonging to the sample, because all those fi's will be 0 for the units which are not captured by the sample. But it's a very convenient matrix notation, F transpose Y divided by little n. F is the vector of frequency counts F1, F2, F capital N. Y is the vector of values Y1, Y2, Y capital N. So this is a very convenient notation Y bar, which is summation Fi yi by n, that is written as F prime y over little n. This F is the vector of frequency counts, Y is the vector of population values of the study character capital Y. Note that any yi, as I said, is observed in the sample only when the corresponding Fi is positive. Next, you also note that under with replacement sampling, the sample vector F follows a multinomial distribution with the parameters small n, that is the summation Fi, and 1 over capital N, 1 over capital N, 1 over capital N, they represent the probabilities. If you recall multinomial distribution, rather to say positive multinomial distribution, there is a total sample size and there are so many classes spread over the multinomial. So there are capital N categories here, and every category has probability 1 over capital N. Though if you recall the notations, N, P1, P2, Pn, here all the Pi's are equal to 1 over capital N, because we are working under with replacement sampling. Under random sampling with replacement, all the units have got equal probability every time. Therefore, it is a classic example of F following multinomial distribution with the parameters small n and Pi's are all equal to 1 over capital N. It is a routine task now to evaluate the expected value of f prime y and variance of f prime y. These are easy exercises. For y, you write down the expected value of y as a vector, you write down the dispersion matrix of y as a vector, then apply the simple results on computation of expected value of f prime y and variance of f prime y. In a way, one can show that expected value of little y bar equal to capital Y bar. This is what you stated already, that little y bar is an unbiased estimation of capital Y bar. Here is a mature way of proving this result. Expected value of little y bar equal to capital Y bar and variance of little y bar equal to sigma square by n, small n, and the expected value of small s square equal to sigma square. All these things follow from the computation of expected value of f prime y, variance of f prime y. In a way, these are mature ways of deducing these results. Where of course sigma square is the population variance with divisor capital N and small s square is the population variance with divisor small n. You must note that these are the quantities used in the context of with replacement sampling, but in context of without replacement sampling, the divisors are little bit different, and we talk about sigma square and capital S square as was introduced earlier. So there is some abuse of notation as against without replacement sampling, but these are always clear from the context. This y bar star, the results on y bar star, that there is a claim that y bar star is also unbiased, that y bar star has a smaller variance than y bar, that is, these results are less transparent. And I want to deal with these things little bit, and then I might take up some non-trivial questions at the end. So it is a non-trivial exercise to show that under with replacement sampling, all the capital N to the power small n samples, they can be partitioned into small n categories C1, C2, Cn. We are assuming that small n is less than equal to capital N. This C nu is a typical notation here. C nu contains all samples of size little n with exactly new distinctive units, nu ranging from 1 to small n. So this is our first observation, that in the context of with replacement sampling, we know the sample space has capital N to the power small n samples, and those samples can be partitioned into small n categories, and the newest category contains samples which are of size little n, but each of these samples has exactly new distinctive units built in it. So moreover, this C nu is also can be shown that it is a collection of all n choose new samples of size nu from the population of capital N units, each repeated the same number of times. In this context, you may recall a famous probability problem in Feller's book that is related to what is called the classical occupancy problem. So in this context, note that there is a combinatorial identity. These number n to the power capital N to the power small n, which is the total size of the sample space, that can be related to all those numbers nc nu by this identity capital N to the power small n equal to summation n choose k delta k o n. Delta k o n is nothing but delta k x to the power n evaluated at x equal to 0. That O, even though we are reading as O, that is delta k 0 to the power n, that is nothing but delta k xn, that is written at the end, e minus 1 power k xn. E minus 1 is delta, the difference operator. So delta k xn evaluated at x equal to 0, that is delta k o n, and one can show by doing the regular expansion that delta k o n is nothing but k to the power n minus n choose 1, k minus 1 to the power n plus etc. etc. This delta k o n times n choose k summed over all k equal to 1 to small n, that gives equal to capital N to the power small n. The very interesting combinatorial identity. It is also mentioned in Feller's book. In a way, this suggests that in the structure of C sub nu, there are exactly delta nu o n repeat samples of size little n, and each one involves new distinctive units for each of the nc nu such possibilities. It it is a good instructional exercise for you to check this phenomenon when, for example, capital N equal to 6, small n equal to 3 or 4. So all you do for capital N equal to 6, small n equal to 3, there are 6 cubed, that means 216 sample points, triplets, and you try to show them in a network, and you can see that nu equal to 1 that captures some of them, nu equal to 2 that captures some, and nu equal to 3 that captures the rest. As a matter of fact, 216 you can have a very nice splitting, and when it is small n equal to 4, capital N equal to 6, capital N to the power small n, that becomes 1296, 1296, and that again you can show how the breakup goes for different values of nu equal to 1, 2, 3, 4. And once you have understood this thing, you can see that conditional on nu, for every fixed value of nu, y bar nu star, y bar star, which was based on distinctive needs, that may be interpreted as the mean of new distinctive needs under SRSWR n nu sampling. So remember, the moment you are conditioning on nu, you are capturing that part of the sample space where every unit has every sample has new distinctive needs, and you know exactly how many samples are there. Delta nu O n, n choose nu, and those samples have the feature that all NC nu possibilities are captured delta nu O n times. That is the repeat number for everybody. So in a way, this shows you that you can view y bar star conditional on nu as if it is generated out of without replacement sample of size nu from the original population. So now we can use the well-known results under without replacement sampling, namely expected y bar nu star conditional on nu is y bar, and hence unconditional expectation is also y bar. And variance of y bar nu star conditional on nu is 1 by nu minus 1 over capital N S square. That is the standard result under without replacement sampling. Therefore, the unconditional variance, we apply the E1, V2, V1, E2 principle, and then the unconditional variance will be as is given in the expression number 2 on the top, that will be, or expression number 2 below, that will be variance of y bar star equal to expected value of 1 over nu minus 1 over capital N S square. So in the top, we are showing the results under without replacement sampling, conditional on nu, explicitly dependent only on the samples which are composed of new distinctive needs. That is how we have the results 1 and 2 on the top, and then using those and taking unconditional expectation with respect to nu, we find the results 1 and 2 below. The first one says that y bar star is indeed unbiased for y bar, the population mean. Second one says that the variance of y bar star is expected value of 1 over nu minus 1 over capital N times S square. You must note that this S square and sigma square, they are related through the following relation. Whereas capital S square has a divisor capital N minus 1, sigma square has a divisor capital N, and hence this identity n sigma square equal to n minus 1 S square equal to summation yi minus y bar whole square. So to conclude, we started with an overview of what we already know from our undergraduate studies, namely simple random sampling with and without replacement. Implicitly, we assumed that there is a quantitative study character denoted by capital Y, and we are interested in the estimation of capital Y bar, the finite population mean, based on capital N units in the population. And we are referring to a sample of size little n, we are referring to simple random sampling with and without replacement, and for with replacement sampling, we are referring to the sample mean little y bar based on all units with repeats, and also we are introducing little y bar asterisk or little y bar star, which is the mean based on distinct units in with replacement sampling. And we mentioned that both of them are unbiased, and we wrote down the expression for the variance for both of them, and we stated a variance inequality which says that the y bar based on sample mean of all units under with replacement has a larger variance than the sample mean based on distinct units in a sample with replacement. So, and then there are a lot of things to come up one by one. With that we closed, and then we will take up some sample questions, mainly relating to understanding of the simple random sampling with replacement, partitioning the sample space, getting a clear idea about nu, the number of distinctive units, its distribution and other aspects. With that we will take up some simple questions and MCQs, then we will pass on to the next one. So, as usual we will start with some theoretical questions followed by MCQs. Okay, so SSG, can you please read the question number 1?
Thank you, sir. For capital N equals 7 and small n equals 4, list all possible samples under SRSWR, capital and small n, and classify them according to the number of distinct units, say nu, in each sample. Further to this, show that the frequency distribution of the number of distinct units, nu, so determined. Show further that for each value of the number of distinct units nu in the sample, the collection of samples exhibits a display of samples arising out of SRSWOR, capital N nu, sampling design, with a constant repeat number for each distinct sample of size nu. Find the repeat number in D for each value of nu. Work out mean and variance on the number of distinct units nu. Also compute the expectation of 1 over nu and verify that the expectation 1 minus nu minus 1 over n times n over n minus 1 is less than 1 over small n. Interpret your findings.
Very good. Okay, so let's have some discussion on this. It starts with capital N equal to 7, small n equal to 4, and it refers to with replacement sampling. Therefore, the sample space captures 7 raised to the power 4, so many quadruples, because the sample size is 4, you have got something like, it starts with 1, 1, 1, 1, ends with 7, 7, 7, 7, and in between you have got all kinds of samples with different repeat numbers, and the total number is 7 to the power 4. And then, as you are supposed to classify them according to the value of nu, so nu can be maximum of 4, nu equal to 1, that means all samples are the same thing. So it is 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, like that, 7, 7, 7, 7. So there are 7 samples in the lot corresponding to nu equal to 1. Then I pass on to nu equal to 2, number of distinct units equal to 2, but the sample size is 4. So if it is 1 and 2, then you have to see all possible repeat numbers for 1 and 2. It could be 1, 2, 2, 2, 2, 1, 1, 1. It could be 1, 1, 2, 2. It could be 1, 1, 1, 2. And then it could be, so all kinds of things that can come up for a sample of size 4, corresponding to nu equal to 2. If I say nu equal to 3, then I know the sample has to have 3 distinctive units and there is 1 repeat number. It could be 1, 2, 3, 1, 1, 2, 3, 2, 1, 2, 3, 3, and so on. So that is how you are supposed to classify all the samples based on the number of distinctive units. And you have to show the frequency distribution of the number of distinctive units so determined. You have to write nu equal to 1, how many samples, 2, how many samples, 3 and 4. And those samples altogether, that will give a total of 7 to the power 4. For every value of nu, further you have to show that they really exhibit a repeat of without replacement sampling n nu sampling design with a constant repeat number for each distinct sample of size nu. It's a very fancy exercise. You can see for yourself why you are telling all these things, that every sample for a given nu is nothing but a repeat. In the core it is without replacement sampling and it has been repeated with the same repeat number for all the distinctive units. That is why you can apply without replacement sampling technique the fundamental results under without replacement sampling and derive all the results. So under question C, it says find the repeat number in D, that should be in B. Find the repeat number in question B for each value of nu. Work out mean and variance of the number of distinctive units. Once you have the answer to question number B, which tells you what is the distribution of nu, you can work out mean and variance straight away. And to compute expected 1 by nu, once you know the distribution of nu, we know nu equal to 1, 2, 3, 4. You know the probability distribution. That also you can get from the general result that is given following the identity. So you can use that to compute expected 1 by nu, and then you can verify this result. Expected 1 by nu minus 1 over capital N times etc. less than 1 over small n. To interpret this finding, so these are relating to the variance, and if you are careful enough, you can see they are referring to variance of small y bar, mean based on all units including repeats, and variance of y bar star or y bar asterisk, which is the mean based on distinct units. And this relation in E, that inequality in E, really is heading towards establishing that variance of y bar is larger than variance of y bar asterisk. So if you write that expression, if you write the expression for both the variances, then sigma square s square, if you take care of them by applying the relation between the two, you will end up with an inequality like this, which depends on capital N, small n, and through them an explicit expression for expected value of 1 by nu. So this you can verify numerically for capital N equal to 7, small n equal to 4, and the interpretation is along the line that y bar and y bar star, whereas both of them are unbiased for the population mean, y bar star has a smaller variance than y bar. That is how you interpret this result. Okay, let's read the next one.
Verify that the expectation of 1 over nu is 1 raised to the power n minus 1 plus 2 raised to the power of n minus 1 plus, and so on, plus capital N raised to the power of n minus 1, whole divided by capital N raised to the small nth power for n capital 6, small n 4, and for n is equal to capital N equals 7, and small n equals 3 and 4. And prove the above result for general n when small n is 3.
Okay. Let's take up the part B first. Whenever you tell me small n equal to 3, I can see that the possible values of nu are 1, 2 and 3. For any general capital N, because you are talking about a sample of size 3. Nu equal to 1, that means all the units are the same. So that part captures capital N samples, namely all ones, 1, 1, 1, or 2 to 2, or 3 to 3, all the way up to capital N, capital N, capital N. These are all captured by the fact that for each of them nu is equal to 1. When you say nu equal to 2, if I have I and j are as two distinct units, one of them has to be repeated. It will be either iji or ijj. Now I have to make a choice of all I and j. There are capital N choose 2 possibilities for I and j, and then that follows with I or j separation. Therefore, capital N choose 2 multiplied by 2, which is n into n minus 1. The first part was capital N corresponding to nu equal to 1. The middle part is capital N into capital N minus 1 corresponding to nu equal to 2. The last part is capital N minus 1, capital N minus 2, because you are referring to nu equal to 3. So these are the 3 parts. You have a partition of the total sample size. The capital N to the power small n, capital N cube. And once you see that, then you can immediately compute expected 1 by nu and then verify this result. And then when they are talking about capital N equal to 6, small n equal to 4, you know how many samples are possible. Then it's just a matter of looking at the sample space very clearly, and then you can immediately think of the partition into nu equal to 1, 2, 3, 4, and then you know the samples captured for every value of nu, you know the probability distribution of nu, and you go for this computation. This is a fairly standard exercise, not difficult. What is the next one?
Question 3. Consider capital N equals 10 and small n equals 5 under simple random sampling with replacement capital N small n. An incomplete description of the random sample is given by 3, 7, 2, and so on. Characterize all possible descriptions of the sample so selected. Also, work out the distribution of the number of distinct units in this collection of samples.
Very good. Very good. So the sample size is 5. So we are making 5 attempts to pick up one item at random out of capital N, and it is with replacement, so there is a possibility of repeat. and in my sample there is an incomplete description of the random sample. They are showing only the first three, 372, and the other two are missing. Characterize all possible descriptions of the sample so selected. So once you have 372, what could happen to the others? You already have nu equal to 3. It could be nu equal to 3 or nu equal to 4 or nu equal to 5. These are the only three possibilities. For nu equal to 3, that means I have no more distinct unit. I have captured 2, 3, 7. So the last two are going to be repeats of 3, 7 and 2. So that I end up with nu equal to 3. And if nu equal to 4, I have to think of one more as an additional unit beyond 2, 3 and 7, and then the fifth one will be a repeat of them. And when nu equal to 5, all 5 should be distinct. So I have a way out to write down all possible descriptions of the sample so selected by starting with 372, by expanding the consideration for nu equal to 3, nu equal to 4, nu equal to 5. And once I know that, I can work out the distribution of the number of distinct units in the collection of samples. I know nu equal to 3, 4, 5 and what is the distribution. Conditional on 3, 7 and 2. This is an interesting problem in probability, very easy problem. Next one.
Work out the expressions for the first and second order inclusion probabilities of units under simple random sampling with replacement, capital N, small n, sampling procedure, and also under simple random sampling without replacement, capital N, small n, sampling procedure.
Very good. So let's have some discussion on that. Okay. These are simple questions, not at all difficult. Exercises in probability. What is the inclusion probability? Inclusion probability of an unit. Under random sampling, for example, whether it is with replacement or without replacement, there is no absolute guarantee that, for example, unit number 1 will be captured in the sample. There is no absolute guarantee because you are working under random sampling. And under without replacement sampling, your small n is less than, strictly less than capital N. And under with replacement, even if small n is more than capital N, because it is with replacement, there is no guarantee that unit number 1 will always be captured in the sample. That's why the notion of inclusion probability comes. The inclusion probability of unit number 1, what is the chance that unit number 1 will be included in your random sample? And that is the first order inclusion probability for unit number 1, 2, 3, taken one at a time. When we say second order inclusion probability, we are referring to the joint occurrence. Unit number 1 and unit number 2, what is the chance that they will occur together in a random sample? That is referred to as the joint inclusion probability of units 1 and 2, that is called second order inclusion probability. So we have to work out the first order inclusion probability and second order inclusion probability under with and without replacement sampling. I have explained to you the notion of inclusion probability. The rest is a very simple but interesting homework on computation of probability. I won't elaborate further and I hope you can work it out. Let's get to the MCQs, please.
Under simple random sampling with replacement, capital N, small n, the number of distinct units nu arising in any sample may assume the values 1, 2, and so on until small n. Is it always true? Not always true, or does the relation depend, or does it depend on the relation between small n and capital N?
Okay. So should we discuss the solution? I am sure the solution is already given here now. Oh yeah, I have the solution here. Okay. So no problem. But anyway, you can discuss. Okay. It says with replacement sampling. So that is the catch. If it is with replacement sampling, even a single unit may be repeated all the time, no matter what small n is as against capital N. It could be, capital N could be 10, small n could be 15. So you are taking samples one by one with replacement 15 times, and you may end up getting unit number 1 all the time. That is always a theoretical possibility. It says the number of distinct units arising in any sample, it can assume all the values 1 up to small n. If small n is unduly larger than capital N, it cannot happen because number of distinct units is always covered by capital N. Capital N is the upper limit. So this statement cannot be always true. If small n is larger than capital N, this statement is not true. It is not necessarily true. Truly, it depends on the relation between small n and capital N. So that is the closest answer. What about question 2?
Consider capital N equals 12 and small n equals 5 under simple random sampling with replacement capital N small n. An incomplete description of a random sample is given by 3, 4, 3, and so on. Toward characterization of all possible descriptions of the sample so selected, the number of distinct units in this collection of samples has a distribution ranging between A, 2 to 4, B, 1 to 4, C, 1 to 5, and D, none of the above.
It's a good question. I won't get into any discussion on this problem, okay? You can take it up. What is the next one?
Under simple random sampling with replacement capital N small n, with capital N equaling 20 and small n equaling 4, a sample contains mu equals 3 distinct units. Then the number of such samples of size 4 is given by A, 20, 19, 18.
20 into, that's a multiplication, huge number. 20 into 19 into 18 into 4. There are 3 options given and the last one is none of them.
None of them.
You are supposed to find out how many samples are there if the sample size is 4 and if it contains 3 distinct units. So we have a formula, you can also apply the formula and get it. Okay.